Now it's time to put all our information into practice and start graphing some rational functions. When you're prompted to graph a rational function, I will always ask you for the domain, meaning the domain exclusions for the function, the vertical asymptote or asymptotes equation or equations, whether the end behavior is horizontal or slanted, and then that asymptote equation, as well as the x and y intercepts. We haven't discussed those yet because, well, we've talked about them before, and you find them the same way here, and now I'll show you how to do it for rational functions. And then the grid where you'll be constructing the graph isn't actually on a proper grid. You just have equally spaced tick marks on the x and y axes, so that way you can framework your vertical asymptotes as dotted lines and your horizontal or slanted asymptotes as dotted lines, plot your intercepts, and then, make the connected graph based on the framework you've made with the asymptotes. So in this first example, the domain comes from the values I need to exclude from this denominator. This factors as x minus 4 times x plus 1. So the denominator is going to be 0 if I use values of 4 or negative 1. So that means the domain of this function is the set of all x such that x is not equal to 4 and x is not equal to negative 1. Now remember, these domain exclusions and these vertical asymptote equations are forever linked together. If you have any domain exclusions, then you've got vertical asymptote equations, and they come directly from that. This graph will have a vertical asymptote at x equals 4, and it will have a vertical asymptote at x equals negative 1. So we've actually got some stuff that we can plot here. Now remember, vertical asymptotes are used to frame the graph. That's where the graph will jump to positive or negative infinity in the y direction. So they're only used to frame the graph. They're not actually part of the rational function's true graph itself. So what you need to do to represent vertical asymptotes is to just draw some dotted lines on here at these particular x values. So at x equals negative 1, I'll draw a vertical line there that represents the placement of that vertical asymptote. And I'll label it here at the top. That is a VA at x equals negative 1. I have another vertical asymptote over here at x equals 4. So I'll draw another dotted vertical line through the value x equals 4. And note that that's a VA at x equals 4. So that way, when I start to make the graph, I know that this is where the infinity jumps should occur for this function. Okay? So we'll build the graph as we go through. Now, horizontal or slanted in behavior, that's where you have to look at the degree of the top and the bottom. The degree of the numerator is 1. The degree of the denominator is 2. So, referring back to the very handy in behavior chart, if the top degree is less than the bottom degree, then y equals 0 will be your in behavior asymptote. In this case, a horizontal asymptote at the x-axis. So, this will be horizontal, not slanted, and the equation will be y equals 0. It'll be the x-axis itself. Now remember, this only takes its influence on these ends of the graph. It doesn't really take an influence right here. So when you're graphing the horizontal or the slanted asymptote, you really only need its influence on these ends of the graph. They may cross right here in the middle, but I'm going to go ahead and put my dotted line there, anticipating that being a horizontal asymptote for this particular function. So I'll just say that's an HA at y equals 0. Then I just graph right there. Okay. Now for finding intercepts, x and y intercepts are still found the same way. To find x-intercepts, you set y equal to 0 and solve the equation for x. And to find y-intercepts, you just plug in 0 for x, and that tells you the value of y. So whenever I'm starting off to solve for x-intercepts, I want to take the y variable and turn it into 0. So 0 equals, there's my y variable, the f of x symbol, and then set it equal to the function itself, the x minus 3 over x squared minus 3x minus 4. Well, if you're solving an equation like this, the first thing you do is technically cross multiply to get rid of your denominator. Something you can do here in solving an equation. So Here's a handy shortcut for finding x-intercepts on rational functions. All you really need to do is set the numerator equal to 0, because that's the only part of a fraction that actually can equal 0. So for this purpose, you can kind of ignore the denominator. You're just setting the numerator equal to 0. That numerator set to 0 gives me x equals 3. So this graph should cross the x-axis at the point 3, 0, just by setting the numerator equal to 0. So there's the origin. X equals 1, 2, 3 is there, pretty close to that vertical asymptote, but that's where our x-intercept is supposed to be located. I'll denote that. And our y-intercept is always easier. Y-intercepts are found by just plugging in x equals 0 for all the x's that you see. So you're just calculating f of 0, which will be 0 minus 3 over 0 minus 0 minus 4. So you end up dividing negative 3 by negative 4, and you get 3/4. So the y-intercept is going to be at the point 0, 3/4, or about 0.75. Well, no, that's exactly 0.75. So that means you're going to cross the y-axis at about, let's see, that's about a half, so 3/4 would be about right there. So I'll say that's the point 0, 3/4 for my y-intercept. Okay, now that's all the information we've got. So if you need to refer to the calculator graph, you can go ahead and do that to help you piece everything together. Based on these 2 points, though, and based on the way that I know that the graph's going to be close to this line on the left, and it'll have to be coming from positive or negative infinity on these vertical lines, I'm pretty sure the middle part of the graph is going to look like this. It's going to come from positive infinity. It's going to catch that y-intercept at 3/4, come catch this x-intercept at 3, and then it'll have to go to minus infinity because it doesn't cross the x-axis anymore. And since that vertical asymptote is coming up, I know that that's going to have to be the behavior that it exhibits. Well, now there needs to be graphs here and here as well, because you should see a connected continuous graph everywhere except at the vertical asymptotes. So this is where referring to the calculator might come in handy. So let's type this one in. This is parentheses around x minus 3, and then denominator is x squared minus 3x minus 4. So then let's see what the graph looks like in Zoom Standard, Zoom 6, compared to what we've got so far. Okay, so between these two vertical asymptotes, I'm right. It actually does come from positive infinity, has to catch that y-intercept, has to catch this x-intercept at 3, and then has to continue down to minus infinity right there. So we got the middle part just from knowing where the intercepts fell. These other two parts, without knowing calculus, it's probably best to refer to your calculator to get the actual appearance there. So, producing this part, notice, from the left, you got to look at what your end behavior graph is. The end behavior is dictated by y equals 0. So as you come in from the left, the graph should be close to the x-axis, and then as it gets closer to this vertical asymptote, it's going to go down to minus infinity. So this left portion of the graph should look something like this. Draw my arrow close to the x-axis, and then it eventually kind of tapers down and has to go to minus infinity on the left side of that first vertical asymptote, like that. Okay? Then we've got the middle part graph correctly. It makes the jump to positive infinity, catches the y-intercept at 3/4, catches the x-intercept at 3, and then continues to minus infinity just when you get to the second vertical asymptote. Well, now there has to be a graph over here on this side as well, and according to the calculator, it comes from positive infinity, and then, sorry about that, screen went blank, and then comes down, and then notice it doesn't cross the x-axis again because we only found one x-intercept. So when the graph appears to get close to the x-axis, don't make the mistake of crossing it. Remember, this is your horizontal asymptote end behavior. The graph will come down here, get close to the x-axis as it continues on to the right, and they just kind of taper off almost horizontally. and looks something like this when you piece everything together. So you do need to refer to your calculator every once in a while. You will have access to your calculator when graphing these rational functions on the homework as well as on the test. So make sure you're acclimated in, deciphering all the information and, producing a good graph that represents the function itself. Okay, next video we'll show you another example.